Now it's time for me to introduce today's speaker. Today's webinar is going to be given by Michaela Blott. Michaela is a distinguished engineer at Xilinx Research in Dublin, Ireland. At this company or at this institute, she has a team of international scientists that are driving exciting research to define new application domain for Xilinx devices, such as machine learning in both embedded and hyperscale deployments. She earned her MSc master's degree from University of Kaiserslautern in Germany and brings over 25 years of leading-edge computer architecture and advanced FPGA and board design in research institutes such as ETH Zurich and Bell Labs, and also development organizations. She is heavily involved in the international research community, serving as technical co-chair of FPL 2018, DATE 2020, as well as workshop organizer for H2RC. But also she's industry advisor on numerous EU projects and a member of numerous technical programs such as FPL, IS, FPGA, DATE, etc. Most recently, she won the Women in Tech Award 2019. In this talk, Michaela will discuss examples of extreme forms of specialization that help scaling CNN inferences to hundreds of millions of inputs per second to handle machine learning workloads in novel applications such as network intrusion detection. So at this moment, I would like to welcome Michaela. Welcome for joining us, and good, is it afternoon or is it morning?
It's around lunchtime.
So I would say good afternoon. So welcome to this webinar, and the floor is yours.
Good afternoon, good morning. Hello from Frosty Island. Okay, all right. So I hope everyone is doing okay during these crazy pandemic times. I'm delighted to be here today and being invited to the seminar series. And I'll talk to you about scaling DNN inference for extreme throughput applications. So this subject is very much at the heart of the research that we're carrying out. But before I get to the interesting bit, I would just like give you a 2-minute introduction with a little bit of background, just so you can understand my background, my perspective, and also to introduce the basic terminology for the rest of the talk. So as Thomas already mentioned, I work for a semiconductor company by the name of Xilinx. I'm just checking why the slide advancing is not working. Okay, is about 30 years old and probably most well known for inventing the FPGA. I'm heading the European Research Organization in Xilinx, which is just about 10 researchers in total, plus a couple of guys in the university program. We, if I'm allowed to advertise, we have a highly active internship program with, even during pandemic times, typically 4 to 6 master's/PhD students with us at any stage. The focus of our efforts is FPGAs and machine learning, whereby we have a very hands-on approach. So we're building full systems, we're doing architectural exploration, algorithmic optimizations, and benchmarking, all with the overall aim of quantifying the value proposition of our devices in this space. So, and all of this is done actually in collaboration to really make sure that we're always on top of state of the art. So let's spend a minute also and talk about what are FPGAs. While I realize many of you might know this already, I just want to make sure I'm not leaving anyone behind during this talk. So the FPGAs are custom hardware circuits for your applications, but unlike ASICs, you can actually reprogram them. So you can adapt FPGAs to customize I/O interfaces, computer architectures, memory subsystems in whatever way to meet the specific requirements of your application. So the typical use case is you have a board like I'm showing there on the slide. Let me switch the pointer on as well while I'm at it. And you need a device that fits in the middle here, and there's just nothing on the market that will actually fulfill your requirements. And you really don't want to do an ASIC because the ASIC is too risky or it costs too much money. That's when you actually use an FPGA. So how do we actually implement these FPGAs? So they consist of a sea of lookup tables, or LUTs for short. And to give you a feel for it, we're talking millions of LUTs in the latest generation devices. These are interconnected with a 2D fabric, which is programmable and provides an extremely high number of cross-sectional bandwidth. Everything is surrounded by the programmable I/O. And then we have more specialized compute elements embedded inside the fabric, such as DSPs, which would handle n-bit multiply accumulate operations. In addition, we have a lot of on-chip memory in form of blocks of SRAMs, which are dispersed over the fabric. And that is in essence what forms a monolithic FPGA on one compute die. With more recent generations, since 28 nanometer family, we are actually found a way of putting multiple of these dies within one package. The idea is that we're using multiple of the device, put them on top of a silicon interposer, which provides the cross connectivity. We're talking about 10,000 lines between these individual blocks. And that technology is called a stacked silicon interconnect and allows us to scale the capacity of the devices to a certain degree. So that's as much of the background that I actually need to introduce. So on to the fun subject now. Let's talk about DNNs and communications. So DNNs are becoming increasingly popular in numerous application domains because either they can solve problems better than any other algorithm before, or they can solve problems that actually haven't been solved before. And that also applies to the communication space, where we see many emerging use cases, from traffic classification to monitoring, prediction, network intrusion detection, and full physical layer implementations. We also observe the application of DNNs to implement individual basic components within networking systems, for example, for hash tables or for certain sorting algorithms. And I'm sure I'm missing some of the use cases. I just noticed that the ITU has identified and classified 30 use cases. So in this talk, we're only focusing on one of them, which is network intrusion detection. There are very specific challenges that we encounter when we're bringing DNNs to communication systems. The first one I observe is certainly the throughput requirement. So within wired telecoms in particular, where you have, for example, a 400 gigabit per second Ethernet rate, you're looking at extreme high inference rates. So if you assume just 64 bytes by packet, then you would have to deal with 600 million requests per second. Even for 5G, when you're targeting, let's say, 20 gigabit per second data rate, you would still have to look at a throughput of 30 million requests per second. So that is way beyond to where we currently are within the computer vision space. So if we look at the latest numbers published by the industry benchmark MLPerf from this summer, where the best numbers from the industry have been presented, we look at a ResNet 50 classification rate of 55,000 frames per second. So that's 3 orders of magnitude like below on what we actually need in the context of communications. Now, I realize we don't necessarily need to deploy a full ResNet 50 in a 400 gig Ethernet line, but there's certainly implications on the size of the neural network that we can deploy. So even at a 1 million operations per inference, if you had a model which was in that category, you would still require 600 teraops for processing 400 gigabit per second line rate. So there's no doubt about it. The throughput requirements are just extremely high, and they're going to be at the limit of what the latest AI silicon actually deliver. So the second specific challenge that we see within the DNNs in the communication space is the latency requirements. So this doesn't apply to all of the application scenarios, but certainly those where you have any form of cognition cycle or some form of control loop, as you would have, for example, in the context of network intrusion detection. So the example is basically you have a link coming in, you're classifying all of the traffic, and then afterwards you're going to make your decision whether you're going to drop or pass the packet. Now, while that decision is pending, I have to buffer all the incoming traffic at the same rate. Now, if this is a 400 gig line, then this is like drinking from the fire hose, and I need to keep the data somewhere. So if I would take 1 millisecond just to make my decision here, then that translates into 400 megabit of buffer requirements. Even for the 5G scenario, I'm looking at 20 megabits. So this is a real strain for semiconductors. Now let's take this back and compare it again with the best numbers from the computer vision space. Here the best numbers in the summer were in the closed data center single stream latency category, 2 to 7 milliseconds. So that's like beyond to the right in terms of latency category and the amount of data that we have to buffer here. Now, all of these challenges couldn't come at a worse time for the semiconductor industry. We're all battling with reaching the end of Moore's law, which means that we're in essence hitting manufacturing difficulties of shrinking transistor sizes beyond 5 nanometer. So FinFET, which is our typical transistor technology, doesn't scale to 3 nanometer. So just to make it more specific, oh God, I can see this might be a little bit hard to read, but trust me, this is the 7 nanometer family. This is what we're currently shipping in Xilinx, for example, and we would be always close to the edge. The next generation node is 5 nanometers, and after that, it's not clear how we're gonna get there. The second problem relating to this are the exploding design costs. So this chart actually shows design cost on the y-axis. You can see that it's exponentially growing. Now you might not be able to read the numbers, so let me do that for you. So at 5 nanometer, you're looking at $540 million for creating an ASIC in a 5 nanometer technology node. So if you imagine that you would be a hardware, an ASIC startup in the AI space, in order to make any profit, you have to amortize this design cost of $540 million that you're actually starting off with, and that is a challenge. The third problem is that we're getting limited performance and power benefits with smaller technology nodes. So if you would go a few generations back, there would be always some benefit by shrinking the transistor size in terms of clock performance, power, and space. And that benefit gets smaller and smaller and smaller. So putting it simply, we're hitting the limits, the physical limits of where we can go with silicon-based computing, and we have to move away from standard von Neumann architectures. So we just can't keep doing what we've been doing all the time by just shrinking it, putting more cores into the same device, and then hope that through the shrinking technology size, we're getting some sort of scalability. So architectural innovation becomes paramount, and this is exactly what we're seeing now happening in the industry. Seriously, computer architecture hasn't been as exciting as it is at the moment for a long time. There's so much innovation going on. Let me actually start with some extreme examples in the space. So the first one, and that's probably my favorite, is from Cerebras. They have pioneered this concept of wafer scale computing. So just as a quick refresh, semiconductors are being manufactured by being printed on these wafers. The wafer is then cut up into the individual compute dies, which are then packaged and shipped. So what Cerebras innovated is a way to actually interconnect the individual dies. You can see them here in the picture to each other, and then you don't break up the wafer anymore. So you just trim it a little bit around the edges, and then you package the whole wafer as a chip. So this gives you chips the size of dinner plates. Just compare this to the largest GPU device, which is on the right-hand side shown here, and it looks minuscule compared to this. So the GPU has 21 billion transistors, which is already a phenomenal amount. The Cerebras device has 1.2 trillion transistors, right? That is mind-blowing. So you think, oh yes, so we're sorted, that'll solve the problems that we're facing here. But in fact, this is still very speculative. So there are many challenges regarding packaging, testing, supply chain, yield, and so on. So, but a really cool idea, going wide. So instead of going wide, we could also go high. So with die stacking, where we're putting all the dies on top of each other, and there are a number of semiconductors investigating in the space. In fact, memory vendors are doing this already for HBM and HMC. But there are serious challenges associated with this when you're going to stack compute dies on top of each other, all relating to heat dissipation. So it's still speculative. And then you have quantum computing approaches, you have analog approaches. So there is a huge spectrum. What we're focusing on in this talk are actually much more down-to-earth approaches where we are specializing in the compute fabric. So this is something we can actually implement today. And also, this is not a new thing. So this has been already done for a number of years in different application spaces. So not just for deep learning. Let me give you an example from the Xilinx world. So here you can see an FPGA device from a few years ago. What we started doing is introducing more and more hardened functionality. For example, hardened memory subsystems, networking IP in form of media access controllers, so not multiply accumulates. Hardened memory controllers, HBM, analog mixed signal, GPUs, DMAs, and so on. And even more recently, new types of compute fabrics, which consist out of VLIW processors. And these have hardened instruction sets for AI and 5G. So again, here you see we're specializing the compute architecture. And by doing so, by hardening and specializing in functionality, we can achieve performance, scalability, and save power. And this is the type of specialization we're going to talk about now in the rest of the talk. In the context of deep learning, we refer to these architectures as deep learning processing units, or DPUs for short. And there are numerous companies operating in this space. So there's a whole selection of startups such as Habana, Nirvana, Novovidius, which got acquired already. And then there are startups which are still independent, such as GraphCore Wave Computing. There are hyperscalers, Huawei, Alibaba, Google, AWS, Inferentia. I mean, all of them are doing, meanwhile, their in-house ASICs to address the compute loads in AI. And you even have Tesla as an example of an automotive company. So broadly speaking, I categorize, oh, actually, before I get there, let me also address GPUs briefly. So I used to have GPUs always as a separate category. SIMD-based vector processors, but even GPUs have started to specialize much more and more for AI workloads that I would argue actually at this stage, they also fit more into the DPU category. So broadly speaking, we can categorize these DPU compute architectures around an axis of specialization. So here in the chart, so if this is my spectrum, to the far right, I would have the most specialized devices, which will, because they're so specialized, give you the highest performance, highest throughput, and would be the most efficient. On the left-hand side, I would have the most generic devices, which would perhaps be a little bit slower, but they would provide you with a greater flexibility of workloads that they can actually handle. So I've introduced 3 categories of computer architectures here. On the far left is the matrix of processing engines, which customize for DNNs in general. Then I have the spatial processors, which customize for the specifics of a topology. So you could, for example, have a ResNet 50 accelerator. And on the far right, we have the extreme variants, where the topologies are fully code-assigned for the hardware architecture. Now, while I have 3 separate categories here, it is actually a continuous spectrum. Let me also say at this stage that you could implement any of this with either an ASIC or an FPGA. But the further you go to the right, the more specialized you're getting. That means you can solve less use cases, which means if you were to be an ASIC vendor in the space, you would get a lower production volume, which means it makes it harder to amortize the initial design costs that I mentioned on the earlier slides. So the more you go to the right, the more likely you are actually going to be to using an FPGA. Let me also talk back about those communication requirements, right? If you remember the line rate requirements and the requests per second, right? We were talking between 30 and 600 million requests per second. That really puts us on the right-hand side of the spectrum of DPU architectures. So let's zoom into the first one, the matrix of processing engines. And that is certainly the most popular approach that you're going to see being used. And I'm really giving a helicopter view here. This is grossly simplified, but I think it's good to look at it this way. It brings a point across. So these devices typically look like you have a matrix of processing engines, which could be broadcast arrays or systolic arrays. And the processing engines could be as simple as just a multiply accumulate, could be a VLIW or a vector processor. You have a certain amount of on-chip buffering and DMA to an external memory system. These architectures typically execute a form of layer by layer compute, where you initially load in a batch of input images, then you schedule the compute from the first layer onto the matrix of processing engine, buffer the results, compute the second layer, the third layer, fourth layer, and so forth, okay? So in order to get compute efficiency out of this device, you need to batch input images. So for example, if you would take layer 4 and that only takes 4 processing engines busy, then you would have a compute utilization of 25%. So in order to really get a high utilization, you would have to process 4 input images at the same time. And this is important. I'll get back to that in a moment. These architectures are specialized processing engines in that they specialize only the operators that you see common in DNNs. So you would, for example, support multiply accumulates, which are very popular. But if you don't have a log functionality in many of these applications, you wouldn't implement that hardened in the accelerator. They also specialize in the form of ALU types, you know, whether they're tensor, matrix, or vector-based. So let me dive a little bit more into detail on this point. So this would be as simple as a vector processing engines, right, where you have a number of input registers and a few ALUs. And as mentioned just there, the ALU would only support the common operations that you would see within the DNN context. For a next degree of specialization would be supporting reduced position. So that would actually give you a finer granular access to the register files that you have. And in order to increase the compute performance, you would actually add additional ALUs or multiply accumulates or whatever you want to do here. The next level of sophistication comes from an improved permutation network, so that you're not only processing adjacent inputs in one ALU, but that you can actually feed one register into many combinations of ALUs here. And that will give you a better utilization across the vector of registers here. And then another form of sophistication was introduced by NVIDIA with the tensor cores, where instead of doing vector processing, you're actually going for matrix processing. So that gives you another level of performance scaling, which would be interesting for matrix multiply. Okay, so then let me just zoom into this point about the batching, because there are fundamentally latency implications as a result of batching, and I think that's really important within the communications context. So let me explain it on the chart here that shows throughput on the y-axis over latency for the neural compute stack executing a multi-layer perceptron. We have done extensive benchmarks. All the results can be found at this link. You can see multiple data points. The first one is for batch size 1, the next one batch size 2, batch size 4, 8, 16, and so on and so forth. You can see that by increasing the batch size, I'm scaling my throughput as expected and as described on a couple slides backwards, right? Until you eventually reach a saturation point where you achieve the very high compute efficiency on your compute array. The batching comes at the cost of the latency. So every time I batch additional images, I'm proportionally growing the latency. And that is something I think we have to be very careful when we're designing for communication application. So let's go on to the next category of architectures now, the spatial processors. So the spatial processors customize for the specifics of the topology. So I would, for example, build a specific accelerator for ResNet 50 or multi-layer perceptron and so forth. The way this is done is that the hardware architecture actually mimics the topology. So in my hardware architecture, I'm going to create the compute for every layer separately, right? Whereby I'm going to match the compute resources that I make available per layer proportionally to the compute requirements that I actually have within the original neural network. Then I'm going to interconnect this all through a streaming fashion, which allows me to process a stream of incoming inputs back to back, right? And because I've balanced out the compute requirements here, I'm going to generate a balanced data flow, and which minimizes the amount of buffering that I have to do in front of every single layer. So this design has additional benefits. It's higher in efficiency than you've seen with the matrix of processing engines, because for this specific topology that I'm running, I've created the exact requirements in my hardware. I only have as much memory there as I need actually to store all the model parameters. I only have the compute there that I really need. Secondly, this is going to be very low with fixed latency, again, because I don't have to batch to achieve a high compute efficiency, and I don't have to buffer in between the layers because I have a balanced data flow. Because this is getting much more specifics, this would be typically much more an FPGA implementation. So there's a specific advantage that you're going to get from the spatial architectures, and that is that I can actually scale to meet the specific performance and resource requirements that I have in my application. So if I take this example of a 2-layer DNN and I create my hardware architecture for this, what I can do is I can proportionally scale down every single layer in my device to fit into a smaller resource footprint. So let's say, for example, I wanted to embed this into an IoT device. This could be very attractive. Now for communications, the other side is probably more interesting, where I can make the hardware architecture more parallel in every layer by giving everything proportionally more compute resources. And I can go that far in this by actually getting eventually dedicated resources for every single neuron, in which case I'm actually talking about a fully unrolled neural network topology and the hardware, which will be able to classify your contents at a clock rate. So the advantage here is that I can scale performance and resources up and down to meet your application requirements. And if I have enough resources on my device, I can actually completely unfold the circuit and scale it out to inference at clock rate, which is where we probably need to go when we're talking about communications. Another popular form of optimization is customizing arithmetic, and which we believe will be actually very important in the communications context. So customizing arithmetic, so the number of bits that I use for individual weights and activations while my accurate tolerates, brings a number of benefits. So first of all, it shrinks the hardware cost of my hardware operators. So instead of implementing a 32-bit floating point multiply accumulate, if I just use a binary multiply accumulate, I save roughly about 100x in hardware resources. And if I have my operator 100x smaller, it means I can instantiate 100x more in my hardware, which, because neural networks are really parallel, allows me to scale my performance by 100x. Second benefit is I reduce my memory footprint. So if you take a ResNet 50, 25 million parameters, if I store that in 4 bytes, I'm talking 100 megabytes, which is too big for most chips, and I have to go to external memory. If I only use binary representations, I can say in most devices on chip. So that's a big benefit because it allows me to avoid memory bottlenecks. And thirdly, it inherently saves power. So here I'm showing the chart from the 40 nanometer ASIC with the intrinsic energy cost per operation. Again, this might be a little bit too small for you to read, but between a 32-bit add, it's 0.1 picojoule, and the 8-bit add, which is at 0.03 picojoule, I'm saving an order of magnitude in energy cost. And the same is true for FPGAs. And at some stage in the future, I will have the FPGA chart here as well. Okay, so let's talk quickly about the granularity of customizing the arithmetic. So if you have a matrix of processing engines, and I reduce a reduced precision operator in my processing engines, say int 8, the implication is, because it is a layer by layer compute and any layer can end up anywhere on my processing engines, that everything, all the way its activations over all of the layers have to have the same precision. On my spatial processing, this is very different because I have these dedicated resources for every single layer in my neural network. I can mix and match any precision between weights, activations, and any of the layers in my implementation. So what that means is actually with the spatial processing architectures, I have much more scope for exploiting custom arithmetic, and therefore derive greater benefit from it. So this was the spatial processing architectures. Let's talk about the extreme specialization now in form of fully co-designed topologies. So we're talking about this effort as LogicNet, and let me explain you quickly the key idea here. So the light bulb moment was with us when we realized there's a neural network. So if you had a single bit output and a 6-bit input with floating point weights, batch norm, threshold activation, no constraints here, that is completely equivalent to a 6-input lookup table that we have as a hardened component in the FPGA. And there are ways to generalize this concept to more inputs and higher precisions. But just to keep it simple, this is the key idea. And what happens is if you have this idea on board is that you can turn the whole problem upside down. So up until now, our approach was that we pick a DNN topology and we train the DNN, whereby in the training process, we adjust the parameters of the DNN while iterating over the training data set until I achieve my accuracy. So then I take the model, I optimize my hardware for it, and I deploy it. What we do now with LogicNet, is the name of our effort, is we actually pick a circuit and we treat it as an unrolled DNN. Then we train this DNN. So again, we are adjusting the parameters of the DNN while iterating over training data set. The parameters of the DN are then equivalent to the contents of our lookup tables. And what we get out of this then is a neural network that can be deployed at maximum performance by design. So this thing will out of the box classify at clock rate. So first results that we got here were from the area of large scale high energy physics, like the ones you run at CERN, where you're basically processing 7 terabits per second of input data. So this is even worse than in the wire telecom space. Secondly, to the high throughput, the requirement is on low latency because we're sitting here in a control loop. And here are the results that we got out of this, which are really promising. So we were able to classify at 427 million samples per second. So that's in the right vicinity for our wired communications problems with 38,000 LUTs and 13 nanosecond latency. So we're going to open source this very shortly as part of a larger project that I'll talk about in a second. But let's talk about now scaling to extreme throughput in the context of network intrusion detection. So here I'm showing a very simplified diagram of a network intrusion detection where packets come in over the network interface, they get processed, feature extraction, going into my traffic classification. And after that, I'm deciding whether to drop or pass the packets, and then they leave my system again via the network interface. So we have 2 implementations of this. One is the fully unrolled spatial processor, so middle category, and one is the LogicNet implementation on the right. And here are the results. So the fully unrolled SP, we used actually a multi-layer perceptron with heavily customized arithmetic, where to be precise, we're talking here about 2 bits per weights and activations. This design is currently in place and route. We're fully confident this will run at 200 million requests per second, which is already beyond the 100 gigabit per second rate with 1.2 microsecond latency. So it's really nice latency, high throughput, right vicinity for communications, great results to begin with. And then we said, okay, let's take a look of where can we go if we had the flexibility to change the topology like we would have to do for LogicNet. So here is where we picked a circuit instead of the MLP. It is very sparse by design, right? So we're talking here 7 inputs per neuron rather than the 64 that we had in the MLP, which makes it much more suitable to the FPGA fabric. And this design runs now at 471 million requests per second, which is in the right vicinity for the 400 gigabit per second throughput requirements. The latency is even better. That's down to 9 seconds, so extremely low, which makes it really attractive. And it runs by design at a high clock rate, which is 471 megahertz in this context. So upshot here is spatial processing, customized arithmetic, and learned circuits can really help to scale your communication systems to throughput and latency requirements that you might have. Now, the key challenge here is how can we actually enable a broader spectrum of end users to be able to take advantage of this technology. And for this, we've created the project FIN. It is aimed to providing tools and platforms for exploration of DNN compute architectures. It is designed for you, for the research community out there. We've created an end-to-end flow that even allows an ML engineer who has no understanding of hardware architectures on an FPGA to exploit these spatial architectures and custom precisions. And it is open source from the ground up to provide the transparency and flexibility to adapt to your applications. It is a number of stack of modular components from a training library, which does the quantization aware training. It can even learn the precision. It has the compiler, the FIN compiler, which generates these spatial architectures, allows them to scale them up and down to meet your requirements. And we have a deployment flow for both embedded as well as server class platforms. We have infrastructure made available at 4 locations worldwide, which is completely free of use, intended to enable the research community. And this is, by the way, not just for machine learning and the FIN effort, but for anything you want to do with FPGAs. And it's just a number of server nodes with high-end FPGAs. So the latest and greatest are in there with a high number of cross-connectivity for even putting multiple devices next to each other. So status here is, there's a lot available, but it's still ongoing in development. There's a number of guys in my team working on this full-time for the last couple of years and continue to do so. At this stage, we're looking to build out the community. And while there's many projects out there, we would love to create this differentiating application portfolio where we really have to deal with these extreme throughput, ultra low latency applications where you actually cannot go with your standard MPE architectures. So if you're interested in exploring these architectures, we'd love to hear from you and love to collaborate with you to actually build proof of concepts for this. And that brings me to the end. So in summary, there's a lot of innovative work going on in the space. Specialization in hardware architectures is key to scaling the performance to meet the requirements in DNNs in communications, whereby FPGAs allow you a great degree of exploration. Spatial processing, customized arithmetic, and LogicNets give you the tools to scale up to 100 to 400 gig. And tools such as FIN are designed to make this technology actually accessible to anyone. So please be in touch if you're interested in collaborating. And for now, thank you very much for paying attention. And I'm more than happy to answer a few questions that you might have.
Thank you so much for this wonderful talk. It's quite interesting to see how FPGAs can be integrated with deep learning or convolutional neural networks. Okay, now I would like to request my colleague Vishnu. Good evening, Vishnu, and it's time for Q&A, so the floor is yours.
Thanks, Thomas, and excellent talk by Michaela. I want to first of all ask this question about, you had this slide where you talked about the 3 architectures, the MPE, spatial architecture, and the extreme specialization. It looks to me, at least from a non-trained eye, it looks to me that as we gain the scalability, as you say, there is also a losing flexibility which is happening. So in my opinion, the use cases that you may see may slightly differ. I think you picked the right one. You picked the right one in terms of the security use case and intrusion detection and so on. Those are line rate use cases. I think they are really good use cases. But my question is, when you look at these different types of architectures, do you see different use cases.
Yeah.
Because
Yeah.
in the
100%,
yeah,
100%
please.
correct. Yeah, you're spot on, right? As you said, as the further you go to the right with the specialization, you lose your generality, right? This is the first thing. So you're actually creating very specific end solutions that have a very limited application portfolio. But conversely, the other point that you brought up, you have many use cases which do not need to process 100 million requests per second, right? Why would you go then with an extreme specialization? And that is very much true. In those cases, you would actually, if you can afford it, you stick with the MPE, where you still retain a certain generality. Think, for example, the Edge TPU or the Movidius neural compute stick, right? They're beautiful example in the space. There are, however, even at the extreme end of the spectrum, you still might get benefit from the extreme specializations because it allows you to shrink the power consumption and the resource footprint. So if you remember that slide with the spatial architectures that you can scale up and down, you can actually make them super small, the spatial architectures. And because you can heavily quantize every weight, every activation, you can make them fit like in, for example, in 1,000 LUTs or something like this, which would be very small embedded components. So yeah, so there's a wonderful spectrum of use cases going on in the space.
Yeah. I think from a telecom perspective, I think this is quite interesting array of architectures that you have. It is quite exciting. I can see that before the talk we were discussing how you went from software to hardware. I can see why it is happening. It is quite interesting. It's quite an interesting field, and it is very addictive. If you ask me, it's quite interesting. So actually,
it's actually I started off. Probably about first when I joined Xilinx, which was 15 years ago, I was actually doing network processing at 100 gigabit per second line rate. And then I was said, you need to go and look at data center applications. And then I started looking at them and I thought, you know what, they actually look the same to me. It's still streaming processing, and hence always the theme of pipeline architectures.
That makes me curious. Actually, this is what I wanted to ask you. So, you mentioned inference at clock rate. This is quite interesting, in my opinion. This is the life goal, if you ask me. Inference at clock rate is quite a challenging goal, and I can see that it is very exciting to get to. I was wondering where I have heard this before. Then I realized that 5 years before, or maybe 3 years before, we were talking about encryption at line rate, and before that there were different set of problems, which always looked at this kind of line rate processing. And I remember the NPU problems. So I think the question is that. Is this set of architectures? Is this the problem that we want to address? That inference at clock rate is a really the future research which is going to happen from your vantage point of view of the research in Xilinx. Would you say that going forward this is the future? Inference at clock rate is the future, or tomorrow? Because yesterday it was something else. So where is it going? Could you tell us?
Well, we're at the bottom of the stack. We're the semiconductor company. I would say the community here are the ones which are really defining the goals on where it needs to go. So we're picking inference at clock rate, because we're researchers and we just want to see how far can we push the envelope. That's kind of the extreme case where we have dedicated resources for each neuron and we can just clock the inputs through. So this is where it comes from us. But ultimately, right, this community are really the ones who are deciding what are the target rates. So we've only seen these rates coming in from the communications requirements as well as the high energy physics. So this is where we've seen these extreme requirements. But I'd love to learn more.
Sure, sure. Actually, there is a question Sergi is asking. In fact, this is a very interesting question for ITU as well. Let me give you a 2-minute background. So basically, we worked on something called a serving of ML models. So serving means that you have a trained model, and now you want to deploy it in the network, and that deployment may be in a GPU, maybe in a FPGA, or any other platform that you have, even a CPU. So this abstraction of from going from a trained model to the deployment platform is a problem for us, because it has to be standardized. We want to make that abstraction where the designer did not worry about the deployment platform. This is in general the problem that we attacked last year. So the question is that the flexibility, I think the question is, yes, the flexibility and the reconfiguration aspect is important in this sense. In my opinion, I would like to look at two parts to this. One is understanding, first of all, understanding the capability of the underlying deployment platform. You yourself mentioned 3 of them today. This is to me, if I look at it from a deployment perspective, this is a challenge, because first I want to understand what are the characteristics of MPE, SP, and extreme, and so on. This is a challenge for us. Secondly, if I have, let us say, to pick one of these, can I do it runtime? Now, at the time, okay, I picked it. Now what can I reconfigure in this? This is the question that Sergi is also asking. Is the same question that I have as well. What are
Yes, so if you keep the training of the neural network completely separate from the hardware deployment, right? What scope of exploration do I still have? And what you're going to do is you're going to lose quite a bit of the freedom that you have. So by going the extreme variant is only possible if you can take your own neural network topology, because you create the topology and put it at the problem. So this is kind of the ultimate dream of co-designing, right? So you can't do that if the network, the trained model is fixed. So once you have the model fixed, you still have the scope of exploring spatial processing as well as MPEs or GPUs or CPUs. So that is the, then you, that's the scope of computer architectures that you want to explore. You are going to hit issues with regards to the customization of the arithmetic as well, because there's so many different variants of int8 representations that are being used. So you have to be very careful that they're actually sufficiently represented within the training framework. So it's something to watch out for. There's also another question whether you can actually afford to carry out direct quantization. Yeah, but I think in essence, what's gonna happen is you're gonna lose a lot of the flexibility in exploration and a lot of the opportunities for optimizing. I would also say, so from having worked on quite a lot of examples in the embedded space. So in the embedded space, we have environments which are much more constrained in terms of power consumption, resource constraints, and we typically deal with embedded solutions which are much more heterogeneous. In this space, you cannot afford to go away from co-design. Co-design is a fact, right? So it is a question whether that is something. I understand the loss of standard, the issues that you come with losing compatibility between different solutions, but whether it's something you can afford because it comes at a loss of performance capability. So
sure.
Yeah, it's interesting in whether you're looking at MLPerf, the industry-wide benchmarking effort for machine learning. They run into the same issue, right? They have these models that the different vendors reproduce on their different platforms, And there's very strong constraints put into place, which exclude many potential interesting end solution points from being submitted.
Absolutely, absolutely. Yes, yes. I fully understand. In fact, some of the work which we did last year was exactly around this problem of at least understanding the characteristics of the underlying platform so that we can decide what kind of deployment of the ML model can be done. If I know beforehand that what is it? I mean, is it, it could well be co-designed, but what is happening in the underlying layer, if I know it, then as a AI ML designer, I can do a better job. That's the problem that we were attacking. Yes, I think we should talk again. It's a quite exciting problem to have. I think one more question was about the results, which you showed the graph. I think you had this graph where batch size versus performance you were showing. I was wondering why that plateau. That was not clear.
Oh yeah.
Could you explain? Yeah. Of course.
So let's assume we have a matrix of processing engines which has I think I had in the picture 16 processing engines, and I have one layer, and the compute of the layer is minuscule compared to the matrix of processing engines, and I can potentially keep only 4 of the processing engines busy at a time. So what that means is if I would run batch size 1, I would only get a quarter of the potential throughput. If I go batch size 2, I would get half of the throughput. If I go batch size 4, I can use all of the processing engines, and I'm at 100% of my throughput, and this is where I'm going to plateau. If I then go batch size 8, I'm not going to get more throughput because I'm already at 100% utilization.
So would you say that I think you showed that graph with the context of MP, but if you were to look at the similar performance in spatial processing or extreme specialization, how would it look? Is it worse or
flat line?
Is it better?
Oh, sorry, it's actually a vertical line. Because the latency is fixed. The latency is fixed and correlates directly to the length of the pipeline in the hardware implementation. So how many register stages do you have? Multiply that by your clock period, and that is the latency that you're going to get.
That is interesting. That is interesting. I want to ask about the fin that you mentioned. This is quite interesting because ITU ran a challenge. In fact, we are running a challenge. It is going to end in December with a grand finale event. And one of the things which we were doing was to actually provide data as well as this kind of open source tools which the participants can use to solve real life problems. In fact, I do see many of our colleagues here from Tuxel. I see many colleagues attending, as well as there are others who are here who knows what I am talking about. They actually gave us real life problem sets which can be solved using these open source tools by the participants in universities as well as the industry. There is coming to the question, the fin that you mentioned is open source. You mentioned that you have a fin compiler, if I heard that right. Yeah. And also, question is, could it be a kind of a collaboration platform that we are looking at? And what is the current usage? I think you mentioned a couple of them, but I forget. What is the current usage of Fin, the open source that you mentioned, please?
I'm really happy that this came up because I saw the challenge and I saw the ML tool suite that was provided, and I actually thought it could be an excellent opportunity to integrate with Fin, to provide almost a fast path between, the data collection where you train the model and the deployment. So that could really help with fast tracking the end solutions.
So Fin, as we've created this, is much broader, right? We've done many examples in the computer vision space to begin with, right? So we have image classification on Cypher 10, we have YOLO variants for object recognition and so on. We're doing at the moment a lot of speech recognition, keyword spotting, and the like. And we have these extreme throughput applications with the CERN example, as well as the network intrusion detection. So at the moment, there's no constraints on the type of inputs and so forth. And as often it is the case with research, when you start off building something, you don't quite know yet where it's going to end. But what we really found that the spatial architectures and the LogicNets, they shine in these scenarios where you have extreme throughput. This is where you're not going with your standard architectures, where you just can't achieve it. And so we're actually really keen on specializing applications and building up a portfolio in the space. And if this, if the community thinks this is actually useful and something that people would really adopt and work on, we would be very open to collaborate to see whether this could actually be brought together with the ML tool suite that you have put together.
I think, yeah.
Yeah, I'm really keen to see the results of this competition.
Sure. I think this is an exciting opportunity to collaborate. I firmly believe that there is an opportunity hiding somewhere. we need to talk again. But yes, I think from a use case perspective, we have real life use cases. There has been data, even network data, which is given to us by operators, given to our participants by operators, real life data from the real networks. So there is an opportunity which is to solve it by pooling this community of researchers and open source. There is definitely an opportunity. I want to ask you about your view of things. So we discussed about a south side perspective, if you will, because when we look at use cases down, telco use cases down, we talked about how to deploy models and so on to the platforms. I described my problem, but I want to ask you about your side. So if you were to look at an ML model, so what would you want to know about it? I saw glimpses of what you may say. So you may tell me that you want to know the architecture, maybe the number of layers, or maybe the architecture of it, so that you can unroll, as you say, to unroll it and do this processing that you are doing, spatial processing or MPE or whatever. So what would you like to know about the model? The reason I am asking is, in ITU we do look at standards north and south. So if I can call it that. So there is a standard which we have made, a recommendation which is just now in pre-publication, where we are describing the ML model. So if you were to look at it, what kind of description, what kind of metadata, as we call it, metadata?
Do you mean what would be my wish list for the neural network topology?
Of course.
Oh yes, this is a very tricky question, as we all know, because you really don't quite know where it's going to end up. But so very important for acceleration is sparsity. So the reduced, you could see that with the difference between the unrolled spatial processor and the full LogicNet implementation. A key contributor to being able to clock it faster is actually the reduced fan-in on each of the neurons. So sparsity actually makes it much more friendly for spatial processing. And the other aspect is being amenable to quantization. So the benefits that you get from quantizing down to a few bits are phenomenal, right? There's 100x easily in terms of performance scaling if you go from single position down. And it's also the memory bottleneck. It's a huge thing. I mean, many of the implementations run into this memory bottleneck where they can't get the weights on chip fast enough. And if you shrink the parameters down, you can keep them on chip, and it really enables a lot of opportunities. So I think this would be my two top wishes at this stage.
Excellent, excellent. I was taking notes. So yeah,
Thank you.
Thank you so much. This is great input. We learned a lot. Thank you for staying back and patiently answering all the questions, and excellent talk. And we do see opportunity for collaboration. Over to you, Thomas.
Thanks a lot, Vishnu, for the nice chat. And also, I'd like to give a big appreciation to Michaela for making time and being with us. I think it was quite enlightening. And I hope we will continue the discussion about FIN and see how we can collaborate with the AI and Machine 5G challenge.